All right, so we're delighted to have Nastia telling us about the combinatorics of symbol alphabets. Many of you here know, of course, but when I mentioned this morning about shock of these subjects being related to each other, one significant part of the shock was around 12 or 14 years ago now, I can't remember exactly when the branch cut structure of amplitudes in this wonderful theory that we all love seemed to have something to do with these crazy objects called cluster algebras. And that's something that Nastia has discovered, and we're going to hear something about today.
Perfect. Well, first of all, it's great to be back at the Institute, where I had very fond memories of being a postdoc a long time ago. So thank you, Nima, and other organizers for inviting me. So the subject of the workshop is the combinatorics. So I have combinatorics in the title. So I'm going to tell you a little bit about combinatorics of symbol alphabets in N=4 Young-Mills theory. So let me start with the introductory slide. So the theory that we'll be looking at is N=4 Young-Mills theory. And planar amplitudes in this theory have the most amazing structure. So they have dual conformal or Youngian symmetry. They have amplituhedron, which you very well know, and they exhibit connection to cluster algebras. So this is a simple model that likely can be solved exactly. And it also provides a lot of tools and intuition towards solving more realistic theories. So the goal of many of us for the past 15 years has been to try to get as close as possible to solving this theory. So some of these developments are highlighted in a so-called white paper that I put the number here, where I refer you to that paper for also an extensive list of references. So the main character of this talk is going to be symbol alphabets in N=4 Young-Mills. So some of you are very well familiar with this object, but I think majority are not. So I'm going to start with the introduction. So the first thing I'm going to define, so I'm going to try to focus towards mathematicians here. This is a different way I'm giving this talk than I normally do. So I'm going to invite you to think about amplitudes as a certain functions. I'm going to tell you what kind of functions, and they're functions of a particular kinematics. And you heard a little bit from other talks about the kinematics. Then I'm going to tell you, so since I have symbol alphabet in the title, I'm going to just quickly sketch what that object is. What is a symbol alphabet? Then I'm going to proceed and just tell you the answer. I'm just going to tell you what we know. I'm not going to tell you how we know it. I'm just going to tell you the answer. And hopefully you can process the answer. And then once I tell you the answer, hopefully you can try to analyze the answer from mathematics point of view. And I'm going to just show you some glimpse, some properties of the answer. So I'll demonstrate connection to cluster algebras. And in particular, I chose to also talk about tensor diagrams, which some of you know, so, and to some I will introduce. So that's number 3. And finally, just so this is normally I do my physics talk in the other order. I will just tell you a little bit, maybe 3 slides about how has this answer been computed, because there's been a heroic effort by several groups getting this computing this. In particular, Song Hee, who is here. I don't know if he came. So and many of his collaborators, and Lance Dixon and others. So I will sketch a little bit and on that topic. And finally, and that would be towards the end, I'll tell you what are the kind of, so since I'll tell you about the status, then I tell you about a little bit about next frontiers and the things that we are thinking about. And that's going to higher loops and higher points. All right, so very good. So let's start. Gently going into amplitude. So we've heard several talks already. So for my talk, I'm going to do the following. So let's think about a scattering amplitude as a particular function of on certain space. And each amplitude is indexed by 3 numbers, okay? It's number n, that number of particles. So you hear physicists talk about 4-point, 5-point, 6-point amplitudes, etc. So little n. Then we're gonna number 2 is k. That's a helicity sector. So you hear MHV, NMHV, and square MHV. So each particle has plus or minus. That just tells you how many pluses, how many minuses the amplitude has. And then finally L. And you hear physicists talk about tree level, 1 loop, etc. That's a loop order. So N, K, and L. Okay, that's what are the indices on each amplitude. So in principle, using the rules of quantum field theory, we can take an L loop, NK, MHV, and particle amplitude and compute it to for arbitrary L, N, and K. But of course, that's in principle is the key word. So let me now explain so I said these amplitudes are functions of certain kinematics. So what is the kinematics? And this has been already said. So the amplitudes, for the purpose of this talk, you're going to think about the amplitudes as functions of z's. And these z's, there are n of them, and they lie in GR for n. There's a mod c star n minus 1. So, but z's are n points in CP3. Okay? So, oops, what happened? Did it just... Did I lose the... I don't think I did. No signal. Maybe it's okay. No, I don't think I touched anything.
Yeah, I don't think so.
I think it's like talking, so that means we are connected.
I'm just going to make a switch.
Okay, very good. So I'm describing the amplitudes as a functions of certain kinematics. So amplitudes are functions of z's, which are elements of GR4n. And we're going to use throughout this talk Pluka coordinates on GR4n. So this z's, there are n of them. You can make them into 4x4 matrix and take its determinant, or these are the Pluka coordinates A, B, C, D. Okay, so that's the kinematic space. Now, what kind of functions are these amplitudes? So, oops, now I can't go to the next slide. Okay, excuse me. Huh? So.
Right now, you're able to.
Oh, yeah. Okay, yeah. What are these amplitudes a function of? So first of all, n equals 4 Yang-Mills theory is a very special theory. At L loops, these functions have uniform transcendentality to L. So the transcendentality M functions are, for example, polylogs, which I wrote. So Li1 is just a log, and Li-M is defined by this integral. Then we can talk about generalized polylogs or MPLs. That's when you sprinkle some constants here, constants A. And then more generally, starting at 10, so remember I told you about N, L, and K, starting at 10 points, 2 loops, N cubed MHV, there are elliptic polylogs appearing. And I think Jake, I don't know if he's here, is hopefully you'll hear a whole talk about that, and I will mention a little bit about this in this talk as well. Okay, so functions of kinematics, now symbol alphabet. So I'm going to restrict for now my attention to just multipolylogs. So once you have these generalized polylogs, you can talk about symbol. So the symbol is defined as following. So it's defined recursively for log. Again, this is mostly targeted. Many of physicists probably know this. This is targeted on those who haven't heard this. So for define it recursively, for if you have a function log x, symbol of log x is just x. Now, so Li2, let me tell you what the symbol of Li2 is. You take derivative, so you know that derivative of Li2 is minus log minus 1 d log x. So I define the symbol of Li2 as the argument of this log times tensor product the argument of that. And that's how you recursively, this is what this formula, now let's go back. So that's basically the definition of generalized polylogs. Oops. Oh. So d of the function is f minus 1 d log, and the symbol of this is just the symbol of this function's tensor x. So that's the word symbol in the title. Now, why is this useful? Well, it trivializes polylog identities, and basically it's now a standard tool for dealing with the loop integrals. So for example, let's take the well-known identity like this. And then if you take the symbol of both sides, Li2, like I told you on the previous slide, is minus 1 minus x tensor x. Symbol of this Li2 minus x is minus, so you switched x to switched x here to minus x. And then if you use the properties of the tensor product, this is nothing but 1 minus x squared tensor x. And this is, again, using the properties of the tensor product, which I'm not reviewing. This is nothing but tensor of x squared, and that's the symbol of the function on the right-hand side. So the set of objects, so that's a symbol. So you have polylogs on, of z's, of various polykers on z's, and then you take the symbol. And now alphabet, well, given, so in amplitudes, you have some complicated function of some complicated arguments, and a set of objects that appear in symbol is called the symbol alphabet. So you have the function of these plukers, and they could be some, not just plukers, they could be quadratic plukers, cubic plukers, et cetera, and that's a symbol alphabet. And this alphabet, the physical meaning of this is that it encodes all singularities of a function. Okay, so that concludes my introduction. So you learned that the amplitude is a function of kinematics, and you hopefully learned what the symbol alphabet is. So what's the status? Where do we stand in n equals 4? So the status for, so some of this is for some part of this slide is for amplitude, some of it is for the symbol. So let's remember our labeling. Amplitudes were labeled by n, l, and k. So we're going to go high in number L. So at all n, all k's, at tree level, L equals to 0, all amplitudes are known due to, you can write down formulas due to BCFW, which you heard talks about already. Now, if we start going further in loops, for n equal to 4 and 5, these are known to all, in this theory, in n equals 4, the amplitudes are known to all loops due to the work of Baird, Dixon, and Smirnov 20 years ago. And then starting at 6 points, interesting things start happening, and it gets harder to compute. Now, due to the heroic work of Lance Dixon and his numerous collaborators, the 6-point amplitudes are now known through 8 loops, and 7-point amplitudes are known through 4 loops. Okay, so this is really the state of the art, 8 loops. This is 2308. Now, if we go further in n, then the MHV amplitudes have been known through 2 loops over a decade. And recently, due to Song Hee and his collaborators, some progress has been made, remarkable progress has been made, computing some 8 and 9-point amplitudes through 3 and 4 loops. So that's where we are, and it gets very hard, and new methods are required. But already here, we can see a lot of interesting mathematical structures. Okay, so let me just review what is the alphabet. So again, without telling you where that comes from, what is the answer? So as promised, so we're going to start at 6 points. We're not going to talk about 4 and 5 because these are known exactly. So at 6 points, all you can have is the symbol alphabet are just Pluker coordinates, and there are 15 of them. Okay. Then at 7 points, so this is a result of somebody's calculation. So I'm just stating these answers. At 7 points, you have 35 Plukers, plus you start having two sets of coordinates, alphabets that are quadratic in Plukers. So that's something like that. That's 6 and 7, and just life gets much more complicated at 8 points. So this is straight from the paper by Song's students. At 8 points, you get so-called rational letters. So you start getting things that are that could be cubic or quadratic in these Plukers. And more importantly, you start getting square roots of Pluker coordinates, like I've drawn here. And it's also known for 9 points. So just think about this as a list. You're given the list of coordinates, and you want to understand those lists. And I present to you those lists. So this is the 9 point. Again, there are, as you see, there are various rational functions of those Plukers. They get a little bit complicated, but the answer is known due to computation from physics. And again, the square roots of these Plukers start appearing. Okay, so that's what I had to say about the answer and the status. Any questions? Mm-hmm. The square root will have the square roots of this. Yeah. The some square roots of this object will start appearing. Yeah. Okay. Very good. Okay. So next, so now if I just present to you this answer, we can just forget all physics and just try to analyze the answer. Okay. Hopefully, right? So we can try to see what can we say, because why is this an important problem to analyze the answer? Well, because the hope is, if you see the structure for low points for 6, 7, 8, 9, then you can guess. It will be very important to make a guess for more points. So hopefully, if you describe an object, then one can guess, and then physicists can compute, and then that would be a remarkable thing, and you can solve the theory, right? So that's why it's very interesting problem. Okay, so there's been, so we want to ask a question. Is there a description known to mathematicians of these lists that I presented? So, and there's been some work in the past decade. So I'm going to focus on just the blue ones I chose for this. In various, I've given those number of talks on various iterations of various on various of the topics on this list, but for this conference, I decided to just focus on cluster algebras and tensor diagrams, which are related to cluster algebras. But the description is known from tropical geometry, from dual polytopes, from Plabik graphs, from scattering diagrams, and recently, this is actually a recent interesting paper by Song again, from I think last month maybe, from Schubert analysis. Okay, so I will just do the cluster algebra description of this. So, okay, so many of you know that, let me just, for those of you, maybe a refresher, the definition, I'll just review of the cluster algebra. So, but before I do that, the claim that I'm going to make is that the symbol letters on the list, so remember I had 6, 7, 8, 9 points, the lists, that for 6 and 7 point letters that I presented, they're nothing but the cluster coordinates of Grassmannian cluster algebra GR for 6 and GR for 7. So that's a very non-trivial observation, especially, of course, mathematicians who, if they saw this list, of course, they would know immediately, but it took for us, we didn't know at the time. But okay, so let me quickly review the cluster algebra. So let me start with cluster algebra A2. So cluster algebras are defined by a quiver and a mutation rule. So again, a physicist, forgive me. So this is an example of A2. You have 2 knots and the mutation rule, and that's rule tells you all the set of cluster coordinates you produce. So what we would need for the purposes of our discussion is the Grassmannian cluster algebra GR47. In that case, you start with initial quiver, which has some Pluckers in it. And there's a mutation rule, which I just tell you what it is. And then you, by mutation rule, you mutate each of these nodes, and you produce a list of cluster coordinates. That's what the cluster algebra is. And indeed, so you can do this now, this exercise, if you start with GR46 cluster algebra, and you start with the quiver that is drawn here, and then you do your mutations, then indeed you produce, so in this case, there will be 14 quivers, and there you produce a list of 15 cluster coordinates, and that indeed matches the symbol alphabet that I presented to you a moment ago. Okay, so there's a physics description and then completely different description of it follow from the cluster algebra story, a very standard material in mathematics by now. So for GR47, that's also the quiver you start with. And you, in this case, if you start mutating, there will be 833 quivers, and that gives you 49 cluster coordinates. There are 35 Pluckers, and there are 14 more. Remember, this gives you exactly. So the remarkable thing is that the physicists, they first produced this list without understanding where, only after this was produced, we understood that indeed this could be described by the cluster algebra. So now we want to, okay, so now indeed that matches the symbol alphabet that I presented. So we kind of want to move forward, and we want to make an all L, all K, all N statements now from this just simple observation for 6 and 7 points. But it's not as easy. It's not as easy because starting at 8 points, the cluster algebra becomes infinite. So GR for 8 is infinite. And in addition, some symbol letters are not cluster coordinates. They involve the square roots when written in terms of Pluckers. So that's why it's not, hey, we just solved everything. So for that, what can you do? Well, there are many things you can do, and many people have done, and many people worked on this for the past maybe 5 or 6 years. So one thing, let me show you, for example, how do you, so I chose to show you some things. So let me show you, for example, how do you get algebraic letters as square roots from infinite mutations series. So this is also very well known in mathematics, and it just becomes relevant for us. So for physicists, this at some point became as trying to read math papers and using them for physics problems. So that's kind of the thing that some of us have been playing. But of course, to mathematicians, this is well known. So for example, for the GR48, the initial quiver looks like that. And there's now a double arrow. And those quivers with double arrows, the simplest one being drawn here, if you start mutating, then you produce this infinite sequences. However, if you take a limit corresponding to cluster coordinates along this infinite mutation sequence, I'm not sure if that's the correct reference, but that's what physicists cite. In this limit, you can exactly produce those square roots. So that's one ways of getting the square roots. Okay, so and one can check, and that's been done by James Drummond and his group, is that all algebraic symbol letters known to appear at 8 and 9 points, those square roots that I had on the list, are known to be associated with these infinite sequences inside of GR48 and GR49. Okay. All right, so then the next thing I will quickly, I just felt like I want to sketch a little bit. I want to tell you a little bit about, again, this is something well known to mathematicians. There's another, and that's, so this was here on my list. So we are, so this is this blue object tensor diagrams. Again, another way of understanding those lists. Again, our problem as physicists, we have the lists, we want to describe it mathematically. So we just want to find appropriate mathematics that's been developed to apply to physics. We're not developing any mathematics, well, not me in particular. So very useful for this turned out to be these tensor diagrams. Again, they're very well known to mathematicians and been, actually I just learned this would be 10, not 12. So there's something called tensor diagrams. So SLK tensor diagram is a graph drawn inside a disk with n marked points. And all boundary vertices are colored black, and they can have arbitrary valence. And each internal vertex may be either black or white, but should have valence k. And you can associate to each tensor. So there are certain rules. I mean, if you know them, great. If you don't, you'll have to read the papers. But the upshot of this, that these are well-known rules, and to each tensor diagram, one associates a tensor invariant by certain rule, again, well-known. And for example, this is a tensor diagram, and from this tensor diagram, the associated tensor invariant is 1, 2, 3, 4, the blue curve. Okay. So these tensor invariants are invariant under certain Skine relations. So this is for SL3, this is for SL4, again, very well known. And for physicists, this Skine relation is nothing but identities of these sort. Because, you know, for each internal, so remember how this determinant has an epsilon, but for each white vertex, you associate an epsilon, so you can play with these, and these are well known. Okay, so the conjecture, which has been, again, I'm not great with reference, I do the best I can. So the conjecture by Fomin and Pilevsky was that the tensor invariants for certain abrizable webs are in one-to-one correspondence with cluster variables. So a web is a planar tensor diagram, and an abrizable web is a web that can be turned into a tree diagram using Skine relations. So for example, this is an abrizable web. And what we can do is that those lists that I had, we can represent by these 5 tensor diagrams. So that's kind of nice. And we can do the count. So that's, we can do, for example, the counting. So for all the rational letters up to 9 points, these corresponds to this 5 diagram. So it's kind of compact and clean way to understand all those variables rather than producing the list. Very, very nice. So it's a mathematical tool which we just use to summarize our answers. We also, so that's rational letters. So all the rational letters could be summarized by these diagrams. All of them, yeah, Lauren, yeah. So there's a 4. So it's proven for. So they're 1-to-1. So it's proven rigorously for 3, 9, and 4, 8. My understanding. It doesn't. It's not a solution to the problem, but it's a compact way to writing it, maybe. Yeah. So once you start, yeah, I didn't solve. Yeah, we certainly don't solve, but this is more compact and cute way to write those lists. Absolutely. So certainly doesn't solve everything, but that's a formalism known to mathematics. Yeah, in mathematics. Yeah. K has to be 4 for us. K has to be 4 for us. That's why my understanding is it stops at 4, 8. Nevertheless, we used it for 4, 9. Yeah. So it's just a nice way to repackage and summarize. So that's for rational. You know, to me, this list is a cute picture rather than those lists. And then we had also in the paper an understanding of the algebraic letters. So we have certain rules how we define almost abrizable webs. And so I skipped all the details, but there's some rules we were able to produce algebraic letters as well. So I'll just say that this is a nice formalism, and I chose to talk about it here today because that's very close to cluster algebras. So very good. So I told you about cluster algebra description, tensor diagram description of the symbol alphabet. Let me tell you a little bit about something, a little bit also clustery, before I move to a little bit towards physics. So yes, so those alphabets, the lists, can be described by cluster algebras, but there's more. There's more structure that they have, and more structure is called cluster adjacency. And this first was suggested by James Drummond and collaborators, and we had a interpretation in terms of some Sclannian brackets. But essentially, so you think of those amplitudes as some. So I talked about alphabet, but of course, essentially you want to have a function. So you want a word to build a word from those alphabets. And it turns out that two cluster variables appear next to each other in the symbol of an amplitude only if they're compatible, meaning they appear together in a cluster. Okay, so that's called it's a non-trivial statement, and that's called a cluster adjacency. And so far, everything I have been discussing is a loop level. So everything, symbol alphabet, that's like starts at some number of loops, 2 loops in particular. But there's a very interesting analog of this cluster adjacency at tree level. I think Lauren is going to talk about this in her talk. And the statement is that the BCF tiles of the tree amplituhedron are cut out by collection of compatible cluster variables of GR4N, which has been, I should probably remove the word, essentially proven by Lauren, Matteo, and collaborators. So you'll hear about this in detail in Lauren's talk. So I just thought I'd just mention this important property of cluster adjacency. Yeah. So eventually, let me tell you, since I'm talking about clusters, let me tell you a little bit about something else. So we had alphabet, then we had words, but then we essentially want to get to functions. So we want to uplift that symbol, turn into functions, because amplitudes are functions of the kinematics. So to this, it's very important to understand those functions better. So there's 2 descriptions of those functions. So some time ago, we talked about cluster polylog functions. There's a certain particular combinations of functions which have manifest cluster structure in a certain coproduct. Again, I'm skipping all the details. I just want you to know that all of this discussion of cluster structure in amplitudes, in words, and that goes up to functions. And I think more recently, Rudenko defined from mathematical perspective. So we've been basically playing, physicists have been writing those functions, we've been analyzing those functions, very, very physicist kind of approach. But Rudenko started with mathematics, and he has a definition of these cluster polylogs, and he classified certain cluster polylogs. So it's extremely important for these 2 things to meet somewhere, and that has not been achieved. And it's important to understand this better, whether the properly defined cluster polylog functions are related to what we see in physics. Okay, so this is where I am. I'm here. I don't know how much time I have. Okay, oh, that's perfect. Okay, so I told you the alphabet. I told you about mathematical structure. I told you a little bit about cluster algebra connection. And let me tell you a little bit, just a couple slides, because you wouldn't appreciate it, because where does this answer come from? So where does this alphabet comes from? How has this list? So remember, 6, 7, 8, 9 list been computed in physics? So just a few words. So first, somebody did the computation. You start at 2 loops, 6 points. So the true computations have been done of a Feynman in this Feynman-like diagram. So somebody computed 2 loops, 6 points. Then at higher points, there's something called Q-bar equation, which relates the remainder function, the amplitude, I'm not using this word, at nkl recursively to k plus 1 n plus 1 l minus 1. So there's a well-known recursion. It's called Q-bar equation, and that's how Son and collaborators are getting the higher points answers. Then higher loops. So again, we start with 2 loops, 6 points. We go higher points, Son and collaborators, and we go higher loops. That's Dixon's program, and Dixon and his collaborators. So what they do is they start with the alphabet. They start with 6 and 7 point alphabet, and then they impose the physics and mathematics properties. They do it different ways and different conditions. So for example, they assume that only cluster variables appear, and that the variables satisfy adjacency, that there's certain symbol can have certain first entry conditions. So basically, lots of input from physics. They take an ansatz and they do these computations. So it's called Dixon's bootstrap program. And so for example, here I've written, they start with this many functions, and then they impose symmetries. Many of you, maybe not much, heard Lances Dixon's talks through the course of past 10 years. And then so they start with ansatz, impose the physics constraint, and solve these, remarkably, they solve these large linear systems, and there'll be unique solutions. So that's how they're able to get those, 6-point amplitudes to 8 loops and 7-point amplitudes to 4 loops. It's a very, very impressive program. So this was just 3 slides for you to introduce how these computations are done. So now, but mostly I want to spend the rest of my talk talking a little bit about next frontiers. So there are 2 things. What can we say about higher loops, and what can we say about higher points? Now, some of it will be work in progress. Some just what can we do more? We want to be greedy. We want to do more. So. Okay, higher loops. So what would be for some of the questions, higher loops? So the Dixon's bootstrap program starts with the ansatz for the symbol alphabet. Assumes that 6 and 7 point alphabets are complete. There's nothing missing. And then you start bootstrapping based on that ansatz. So can you prove that? That would be the question I would like to address. And then for higher points, more data is needed in order to identify the structure of more complicated amplitudes. And important progress has been made in June by Matthias Wilhelm and his collaborators. And important, for the first time, all 2-loop integrals have been evaluated. So I'll just flash a slide on that. We think the answer. We're trying to understand the answer. Andrzej in particular. We think there's an answer. But I will say more about the Matthias Wilhelm, Unsparing, and Qi Zhang paper. Okay, so let me just tell you about how can we, in principle, prove. So we want to prove that at 6 and 7 points, nothing is missing. All we have is those letters. So, well, from physics, we know that all the information about the singularities of amplitudes are encoded in Landau equations. And we should be able to just use Landau equations to determine the symbol alphabet. And hopefully this is familiar. There's been some revival of this old work. So given a Feynman integral, there are certain equations you can write for it called Landau equations. You solve them, and then you get the solution, which describes the singularities. So for example, for the massless box, and I've written it in terms of the z's, for example, very simple integral of this form, you solve Landau equations, and you have a solution, which is the singularity of this massless box. So 10 years ago, with our former students and postdocs, we basically just took, so yeah, I should say, the integrand, of course, is very well known. So for 2 loops, you can take Yara and Jake and Nima's integral at 2 loops and solve Landau equations. And this is indeed what we've done about 10 years ago. And of course, you immediately start finding spurious singularities. And again, there's a lot of work has been done, but this is again 10 years ago. So at that time, we can use amplituhedron to exclude some singularities. So it's under good control at 2 loops. So what about higher loops? So at higher loops, things get complicated. And one thing that's been useful that we've been looking at are the so-called ziggurat graphs. So again, I quite try to be brief. So it turns out that the singularities for any n particle amplitudes can be written as a subset of those of a very special type of Feynman diagrams called ziggurat graphs. So ziggurat graphs go in odd and even. So this is a 4-point graph. And if you want to do a 6-point, you add a ziggurat. So this is some ancient ziggurats. You can go to Wikipedia. Some ancient constructions in Mesopotamia, which looks like this. So you start with this. You go to 6 by building up this layer. And so for 5s, you start with this and you add something like this. So they're special. All you need to know, they're special graphs. So rather than starting with arbitrary diagram, you might want to start with these ziggurat graphs. And interestingly, the Landau equations are invariant under certain circuit moves. And under those moves, any graph can be reduced to ziggurat. So that's why it's interesting. It's been interesting to look at those. And indeed, so for 6 points, you can start with a ziggurat and do this circuit moves to reduce it to a graph like that. And that matches a 6-point symbol alphabet. Okay? So then one can start playing with this. For example, you start with 7-point ziggurat and do your y delta moves, and you reduce it to a graph like that. So this is already, you see, this is a very high loop result. So this is a 4 loop, and this is a 6 loops, but it all reduces to analyzing Landau singularities of this. And what was interesting is that with our former student and postdoc, we looked at those, and you can just restrict to those. And we found extra letters. So we've been finding, to leading order, we found just the alphabet, but then we start finding all these extra letters. I'll just skip of this sort. And we kind of been puzzled by this because it's like, this is a very high loop order. And if it's true, how do you know? Because in this Bootstraps program, you really make this as an assumption. So we now, not the cluster algebra. No, they're not the cluster variables. So we now have a new poor student who is working very hard. So he's done amazing student, former UTIN student, and so he's basically so we found, so in this work a year ago we found these extra letters, 2 of them, 2 classes. So now he did the following exercise. He started with known alphabet and added those 2 letters, and run the bootstrap. So he incredibly learned all this bootstrap technique within, like, I don't know, a month. And he showed that there's a unique solution that the coefficients are 0 of those letters. But anyway, I mean, you would say, okay, so this is I'm not claiming anything. This is just towards the goal of trying to prove that nothing else appears. So in principle, why am I doing this? Well, these are simpler graphs to start with. So how else are you going to go to high loops? So that's where we are. And yeah, so he found no unique solution. Okay, so now that's what's we've been thinking about regarding higher loops. Now higher points. Okay, so higher loops, we've been trying to prove this alphabet. Higher points. So I think there's been important progress by Wilhelm Zhang and Spearing. So again, I'm just mostly here to advertise their paper because we haven't done much, but we're working hard. Andrzej and Hee-Cheng Wang, who I just showed. The integrand for all 2 loop n equals 4 has been, I should have a reference to Yara and Bougel and Jake and Nima has been known. So it's known integral. Okay, so so there's a double box, pentagon box, and all double pentagon. So what they claim to have done, they claim to have evaluated all of this. So this provides a wealth of data, if true, because just the way, we started with 2 loop 6 points and we produced so much. So it's very important. So to understand these. So because at these, so they had a series of papers starting with just double box. Maybe Jake will talk about this. So the new types of functions appear here. These are elliptic polylogs, and a community of people have been developing the symbol for the elliptic polylogs. It's just, this is just to show you that it gets more complicated. And it seems like they've done it. The key building block in their analysis, in their evaluation of this, is they actually the differential equation that we actually wrote about 10 years ago. The following is that for example, if you take the double box, you can write it as an integral of the 6-dimensional hexagon. So now, recently we made some progress on exactly evaluating this. So all you have to do, well, all you have to do is one fold integral. So for example, so this is, I just copy paste from the paper. So for example, double pentagon is related to one loop octagon integral. Through these differential equations. So if you know this one exactly, you have to do one fold integral and write it down. So we've been, and everybody has been trying to, so it's very important to move this field. It's very technical, very hardcore, but I think it's very important to really understand the answer and analyze the answer, analyze the function, analyze the letters, and because you can, I mean, this is the honest calculation that they've finally, so the integrand has been written, many of us looked at it by Nima et al. It's been known for 15 maybe years. So now it seems like there's been important progress. I should also mention that for these, we've made some progress as well. We have exact formulas for this, and that's based on Rudenko's volume of ortho schemes. So we can, I just want to skip this. I just want to say that all I want to say is that there's been some progress by Rudenko writing down the volumes of hyperbolic order schemes, and using that we are able to present really an analytic result for the one loop scalar and Gon integral in n dimensions, and that's exactly what appears in those calculations. So it's a one loop 6 Gon and one loop octagon. So it's very important to better understand this formula, and I think we hope that better understanding of this. So this is to me a frontier to go into higher points at the moment. So you want to analyze the answer, you want to see the structures, both the letters and the functions. Okay, so that I think is my talk summary. Back to my slide I keep showing over and over. Let me just say it again. Summarize the talk. So the main character we talked about, symbol alphabet and n equals 4 Yang-Mills theory. I presented to you the statement that amplitudes are a function of kinematics. I told you a little bit what the kinematic space is, what the functions are, what the symbol alphabet. Then I presented for you the answer. What is the symbol alphabet for 0.6789 for a certain number of loops as a slide. And then we looked at the structures of the answer, and I demonstrated the relation that this answer could be understood from tensor diagrams, from cluster algebras, etc. And then I just, so that I'm not just making things up, I had 3 slides showing you that there's been a heroic computation deriving that answer in physics. And then the next frontier has been at higher loops, so trying to understand 6 and 7 point derive the 6, at least for us, for the others are different. So for 6 and 7 point alphabet, and then higher points, important progress on the frontier of elliptics. So that's a summary. But before I leave, I just want to say something about math and physics. So I just want to have this. Now, whenever I talk to people outside the field, I want to remind you that the goals of this whole program in amplitudes is twofold. You want to explore the structure of amplitudes, but you want to also exploit the structure to make previously impossible computation possible. And in order to make progress, the whole field lies on, I like this picture by Zvi Byrne, is supported on 2 pillars. And in order to make progress, we need to have support on both pillars. So on one hand, you have the structure, mathematics, symmetry, beauty, whatnot of those amplitudes. But there's a second pillar that we should not forget, is that we want to use those structures to make explicit results useful, and preferably outside our field. So if there's a beautiful, cluster algebra or some other structure, you want to be able to use that to make, to go higher in N, K, or L. Let me just put it in that. So to thrive, one really needs support of both pillars. So that's why I want to conclude with that slide. And this is the very last slide. So the evaluation of just 2 loop MHV amplitudes over a decade has led to a lot of progress, including the introduction of symbol technology, discovery of connection to cluster algebras. This basically technologies enabled a high loop computation that would have been previously impossible. And I think with a wealth of new data that's becoming available, in particular in this elliptic frontier, I think there's been hopefully a lot more to learn. And I will stop here.
Any questions for us? Sure.
If you were asked by a mathematician to give a 1-sentence definition of a simple alphabet, what would it be?
The singularities.
Singularity of an alphabet.
Of a function, yeah.
I was wondering about the status and perspectives for the elliptic symbol calculus. Do you subscribe to the symbol prime approach?
Yeah, that's what is being used. If you notice that I should have had the references. There are various definitions, and if you see, I did put thought. I prepared for this talk, so I did put time, and that's the definition. That's the symbol prime. I think, yeah, that's what I put. Yeah. But I don't. I haven't worked. I mean, I'm just an observer. I'm just trying to learn this. But yeah. So I don't want to say I subscribe, or that's not the vocabulary I want to use. Yeah.
And within a, say, 10 point?
Are you or are you not a member?
Yeah, I'm independent. I'm an independent fellow.
In a specific 10-point calculation, will there be a finite collection of these omegas without asking you for a definition?
Yeah, the person next to you is been trying to understand this. Yeah. So we've been trying to understand yeah, but yeah, it shouldn't be me talking. I just think it's a very important result if true. Yeah.
Alex.
So question. So if you take more and more particles and high loop levels, the symbol alphabet become more complicated. You get square roots, possibly worse things. I'm just wondering, is it possible that it can, like in principle, be as complicated as anything?
I think it could, but I think we believe. We don't. I wouldn't be working in this field if I didn't believe that there would be a good answer. I've worked on this field for 50.
Is very strangely ambiguous because, as Anastasia was explaining, in principle, if not the letters themselves, where they vanish should be associated with the solutions to these Landau equations. Landau equations are a bunch of coupled quadratic equations. You would think by Murphy's law, they could get arbitrarily complicated.
Yeah.
But they don't appear to get arbitrarily complicated. That's the strange thing, but maybe we haven't gone to high enough loops to see them get arbitrarily complicated. The ziggurat graph statement would make you think they don't get arbitrarily complicated, right? Because there's still a finite number of them, even if things get otherwise. It could be the planarity makes it better, for example. I mean, much like with Plavic graphs. Where again, you could draw arbitrarily complicated Plavic graphs, but we know in the end they can all be reduced to a finite number. So I think it's not clear, but I agree. I mean, my zeroth order instinct would be it should get as bad as possible because there are, you're intersecting quadrics.
But maybe you could have a description. Yeah, it could get complicated, but I mean, someday somebody will calculate and because.
Infinite, but we don't see it. I mean, it gets bigger, but it doesn't seem to grow out of control.
But I'm just wondering if anybody tried to get to prove a negative result, So there's like, there's a, like in matroid theory, there is something called no-funeral.
Yes, that's exactly what I was referring to. Yes, that's right.
Realization of matroids can be basically as bad as possible.
Right.
So maybe somebody
It could be
can-
the planarity makes it better, just like as it does for positroids. I mean, that's another example where once you, yeah, anyway, so, but I think we don't know. I mean, I think
But I think any plane n equals 4, we believe in that theory.
I think it depends on multiplicity. Lots of us believe for 6 and 7 seems to be, I mean, from the
7, I think probably not, but yeah.
Category even for.
well, non-planar certainly. I would-
Non-planar, we don't even, nothing on my talk non-planar, that's a whole, yeah.
It's just, sorry, it's just that at high loop order, it can get arbitrarily bad even for fixed multiplicity.
yeah.
So even like just 5, 4, 8 particles, you get the worst crap at every loop order.
But at this time, there's a result in the literature which should be understood and analyzed from mathematics point of view. That's what my take at the, go home and what do I do? So I think that's for now.
So those ziggurat graphs you have, and the star triangle equations, like are they related to the Ising model or the resistor networks? Because the graphs are.
Well, the delta Y, yeah, that's exactly what you have with the resistors. Our students found this randomly a paper on them. So we just randomly were searching math literature and found it. Yeah, so that's all I know about them. Yeah.
Half of the Landau equations are just an electric resistor problem.
Yeah. And there's
You have some quadratic conditions on top of the.
there are some little issues. There's some violation of this Y delta, which is under control, and we've discussed that in the paper. But it's just a set of simpler graphs to start it with that been defined by this basically. Actually, our students randomly were looking through this guy. Yeah, the thesis by this guy. So so that's originally where this came from. Any other question?
Lizzie has a question.
Yeah, I was wondering if you could go back to the bijection between like the tensor diagrams and the cluster variables.
The tensor diagrams, yes.
Yeah, sorry. I was just gonna ask, if there was any sort of like structure to the bijection, or if they just counted like the number of the things, or.
When we were doing this, we were really after algebraic letters. This was just a nice summary. Yeah, I don't know the answer to this question.
What is this?
Why these are, I didn't know. But maybe there's some way to stir. Yeah, I'm very bad with combinatorics, I should tell you. So maybe there's some way to stare at these and try to understand why these, or try to generalize. Yeah, we just summarized this list with this. Maybe, well, yeah. Maybe somebody should look. Yeah, yeah. That's all I have to say. Again, I took the list and drawn the diagrams. But is there structure? Is there more? Yeah, I think that it would be very interesting if you have time. Yeah, to do that. Yeah.
I have kind of a general question, or maybe something to comment on, but also a comment. I mean, I think there's a zeroth order thing which is crazy here, which is that the amplitudes are functions of these n4 vectors, functions of these blue curves.
Yeah.
And the claim is every place where the amplitude has a branch point is associated with some cluster variable going to 0. Now, why the hell did the cluster variables show up in that question? It's not remotely obvious why cluster variables should show up in this question. The only other place, the only other place we have some sort of analog of this, so why should the external data care in any way at all about the cluster structure? Well, we do see that in the definition of the amplituhedron. It's very, very important when we define the amplituhedron for reasons related to what we saw in Pasha's talk and many others, to have some positivity on the external data so that the external data makes a convex shape in some general sense. And that convexity or the positivity on the external data is somehow tied up with the cluster structure.
Why it was reasonable to make sort of conjectures like if you have planar Landau diagrams, then somehow they should not find any solutions inside the positive part, if the external data is positive, for example. That's a sort of plausible kind of mathematical conjecture. But it seems like you're saying that conjecture is false. The fact that you found these non-cluster letters, for example.
Well, we found them as a solution of the ziggurat, you know, you can, but these are particular graphs that we, but
Graphs, they may not show up in n equals 4 Superang mills, but there are planar graphs that seem to have solutions of the Landau equations even inside the positive part, even when the external data is positive. Nice.
Yeah.
Okay. But anyway, just to throw it out there, this is an amazingly zeroth order question. What kind of what on earth could be the reason why only cluster functions of external data?
yeah, but I think it's very important to do what Lauren is doing for high loops. So they have very good understanding of tree, but the loop level statement, I think that would come. I think, Matteo, if you generalize your results to loop level amplitude, I think that's what needs to, so they, yeah. I think they would understand all of that. If you go to high, is it feasible for you to do it?
I understand that at higher loops, it'll involve the loop integration point. And I'm not sure you'll know about, anyway, it's something extra to see what it might mean post loop integration. Anyway, the comment, but that's my question. So
It would be really interesting to understand any of that from the amplitude period, right? So which we don't, right? So.
So running into this amazing fact, do you have any moral reason why this should have been true?
Yeah, I'm not sure. Yeah, but I think I'm working on this field because I believe there's more, and I think there would be more, but I think we should keep working.
Any other questions for Nelson? All right, if not, let's thank her again.